Okay, good. Yeah, well, so let's start all over again. But I think I will make it short now. I mean, you can see there's quite a number of people I want to thank here, and specifically Andrea and Dora for all the work they have done on, well, these very fascinating rocks. Mm-hmm. There we go. Okay, so the Dominion Group is part of the Archean Geological Record of South Africa, and it is not the oldest unit of rocks that we find in the Kap Vaal Craton. Well, the oldest rocks are well exposed in the eastern part and the northern part of the Craton, where we are dealing with granitoid greenstone terrains that form basically the main component of the Kap Vaal Craton that became stabilized at around 3.1 billion years ago with the emplacement of large volumes of granites. And after that time, well, we had stable basement that allowed the deposition of a variety of volcano sedimentary successions on this stable crusted block. And I will be talking about the Dominion Group, which is part of the oldest volcano sedimentary cover succession of the Kap Vaal Craton, which also includes the Pongola supergroup and the Witwatersrand supergroup. So the rocks I'm talking about were deposited in a basin. The exact extent we don't really know, but the minimum extent is kind of shown in this yellow area. If we are zooming in on the Witwatersrand basin, I mean, this is where we can actually observe the Dominion Group. It's situated above Archean basement with the non-conformity, and it's overlain by the Westrand group of the Witwatersrand supergroup. So the Dominion Group in dark brown colors is only found in the westernmost extremity of the Witwatersrand basin. There is a small occurrence of Dominion Group around the color of the Vredefort Dome, but these rocks are quite strongly deformed and metamorphosed. So most work that has been done on the Dominion Group has focused on areas to the west of Klerksdorp, and this is also where we did most of our work. The Dominion Group consists of 3 stratigraphic units. At the very bottom, we have the Rhenosterhoek formation, which is a succession of siliciclastic rocks, a few meters up to several tens of meters in thickness. And sandstones and conglomerates are kind of the main sedimentary facies in these rocks. And they have been quite intensely explored over many, many decades because they contain minor uranium and gold mineralization. Above these clastic sediments, we have several 100-meter thick succession of predominantly mafic volcanic rocks. And this succession is overlain by predominantly felsic volcanic rocks of the Cipherfontaine formation. And this succession, well, can reach up to around 3 kilometers in thickness. And it was dated quite some time ago at 3.07. And since that time, not much more geochronological work was done on these rocks. So I want to introduce the study area, which is situated to the west of Klerksdorp, just off the map here. One area I refer to as the Hart-Biesfontein area, where quite a bit of Dominion Group strata is reasonably well exposed. And the other area is found around the town of Ottosdal, which also contains quite a bit of Dominion Group exposure, although there's quite a bit of farming in the area, so rocks are not always very well exposed. The lowermost Rhenosterhoek formation is exposed in places here in the Hart-Biesfontein area, and it's basically not exposed whatsoever in the autostyle area. Overlying this, we have the Rhenosterhoek Formation. There's no exposure whatsoever in hard Biesfontein area and no exposure in the autostyle area. What is well exposed is the uppermost Cypherfontein Formation, which is well exposed in both areas. Now these rocks are then overlain along an angular unconformity by strata of the Westrand group, and these are then later overlain by rocks of the Ventersdorp supergroup. Basement granite is also not very well exposed, but it has been intersected in many boreholes that have been drilled over many, many decades. And granites have been dated in the past. Lawrence Robb was quite strongly involved in that, also 30 years ago. And Lawrence and co-workers, well, they obtained ages of between 3.17 and 3.03 billion years. We dated a sample of granite from drill core, and we obtained an age of 3.07 for this granite, which is shown here in this core tray. Now 3.07, this age is a prominent age, specifically in the eastern part of the Kap-Vrak crater. There are a number of granites of that age, such as the Synthenic granite, and this is known to be one of the few Archean tin granites around. So yeah, same age here in the hard Biesfontein autostyle area. So above the granite, in places along a thin paleosol, we find these clastic sedimentary rocks of the Rhenosterhoek Formation. And we did some dating of detrital zircons, and the age distribution is seen in this histogram. And the youngest detrital zircons have an age of around 2,995 million years. So this is the maximum age of deposition for the Rhenosterhoek Formation. As I said, this unit has been explored quite a bit in the past because it contains a bit of uranium and gold in quartz pebble conglomerates, similar to the reefs that you find in the Witwatersrand supergroup. And well, here is a mineral resource statement from 15 years ago. You can see the gold grade is rather low, but gold was not really the target for these rocks. It was always uranium that is much more enriched in these rocks. And it was uranium that was mined like 60 years ago or so, until around 60 years ago at the Dominion Reefs mine. When you look at these quartz pebble conglomerates under the microscope, well, they contain a lot of interesting both detrital and secondary minerals some of which are shown here. You see here some nice detrital garnet. Here you see a number of heavy minerals such as columbite. There's detrital uraninite. There's an abundance of other minerals that indicate that the provenance for these rocks was largely highly evolved felsic igneous source, granites and pegmatites. And for our specific interest was on the detrital uraninite grains as well as detrital cassiterite grains. And a few years ago, we were able to date detrital uraninite from these rocks, and they gave an age of 3.18 approximately. So this age kind of overlaps with one of the ages that Lawrence obtained from dating granites of the Dominion group basement. More recently, and still unpublished, we were able to date detrital cassiterite from this unit, and we got an age of around 3.09. So again, this age is kind of close to the age of tin granites that we find in Swaziland, which seem to indicate that there were probably many more tin granites around in the Kapar craton, but which have since been eroded. Okay, moving stratigraphically upward into the Rhenosterhoek Formation. So it's a predominantly mafic volcanic succession that was erupted largely subaerially, and amygdaloidal basalts are the most common lithology in these in this unit. Here is a drill core that may show some pillow structures, but these features are rather rare. For the most time, eruption was in a subaerial setting. And yeah, there's quite a bit of core available. As I said, on surface, there's hardly any exposure of these rocks. Higher up, we're getting into the Cypherfontaine Formation. So the rocks there are compositionally made of dacites to rhyolites, and they are quite well exposed. What we see here is a massive spherolytic lava flow. Here we have a flow-banded rhyolite, which shows some nice flow folding. And here we have volcanic breccia, indicating that this volcanism was at times explosive and gave rise to well, breccias, but also ignimbrites, which are quite commonly observed in the field. Now these rocks, because they're felsic, these rocks are quite closely associated with the mafic volcanic rocks. It's not really the case that you have mafic at the bottom, felsic at the top. No, there is some kind of intercalation between these units. And well, it has long been known that this succession represents a bimodal flood basalt succession. And we did quite a bit of chemical analyses of these rocks. I don't want to go into any detail here, but the chemistry of these rocks is consistent with melt having been derived from subcontinental lithospheric mantle that assimilated basement rocks that fractionated to eventually result in, well, this bimodal succession that is typical even for modern day intracratonic settings around the world. So now, the Cypherfontaine Formation, because it's made of felsic volcanic rocks, contains zircon, although zircon is not very abundant in these rocks. We dated zircons from rocks from the Hart Biesfontein area, and that's shown here on the right. And most zircons over there, they show ages of 3.07. And this is also the age that was reported by Richard Armstrong and co-workers 30 years ago. But now, samples from the Otto-Stahl area tell us a very different story, because there, most zircons are actually 2.96 billion years in age. And in one or two samples, we actually observed two age populations, the 2.96 population and the 3.07 population, which indicated to us, well, that these 3.07 billion year old zircons are actually xenocrysts. They are derived from the basement, and well, in our study, we did actually date one of the granites at 3.07. So the actual age of emplacement of these volcanic rocks, well, we can now say was much later. It was around 2.96 trillion years ago. Intercalated with the felsic volcanic rocks of the Cypherfontaine Formation are sedimentary horizons, and I show them here with arrows. And these sedimentary horizons, they vary in thickness from a few meters up to around 80 meters. And these sediments are actually being mined for industrial minerals at Wonderstone mine. There's another mine operated by Idwala, and this mine is mining highly altered felsic volcanic rocks of the Cypherfontaine Formation. These The sedimentary rocks have been intensely quarried in different places. And here you see one of these quarries where bedding is dipping at a shallow angle, in this case to the west. So here you see the direction. When you look more carefully at these rocks, you see that, well, we are dealing with sandstones integrated with shale. And the sandstones show nicely developed graded bedding. And we can actually see evidence in the sedimentary structures that these were deposited by turbidity currents. Below these sedimentary horizons, and we have here a drone image of such a sedimentary horizon. So below these horizons, the felsic volcanics are quite strongly altered. And if you look at the chemical patterns of this alteration, you see typically an enrichment in aluminium just below the contact with the sediments. You see enrichment in potassium, you see depletion in iron and calcium and sodium and many other more mobile elements. And we interpret those alteration zones as paleosalts. And there are several of these paleosalts preserved in the area. And one specific, quite interesting occurrence preserves fossil spheroidal weathering. So this image was also part of Dora Paprika's thesis. And what you see are core stones of felsic volcanic rock. And there's another core stone over here, surrounded by highly altered felsic volcanic material. And well, here's a Geology 101 image to remind you how spheroidal weathering, comes into existence during, well, mechanical and chemical weathering of relatively homogeneous rocks such as granite or felsic volcanics. Now back to those sediments. As I said before, mostly they show graded bedding, typical for turbidity current deposits. There are shales. There are not many ripple marks preserved in these rocks, suggesting that the sedimentation took place in a relatively, well, let's say, below wave base. There was not much wave activity taking place. And another interesting feature in these rocks are layers of pyrite, as well as nodular pyrite, which shows nice radial textures typical for diagenetic marcasite nodules. When you look more carefully at the composition of these arenites and shales, when you look down the microscope, you see largely a secondary mineral assemblage of pyrophyllite-sericite and diaspore. There's not much of the primary component left in these rocks. There's a bit of primary carbonaceous matter in these rocks, which give them the kind of gray color. There's some trace of diagenetic pyrite, there's rutile preserved. And when you look at the chemical composition of these rocks and compare them with felsic igneous rocks of the Seiferfontein Formation, you see that the composition is very similar, except of course for the strong alteration that these rocks experienced due to quite intense alteration that we now see in the form of abundant pyrophyllite in these rocks. So much of the provenance for these rocks was erosion of highly altered felsic volcanic rock. So the assemblage of these secondary minerals, pyrophyllite-sericite, diaspore, and I put up a reminder of the chemical formula, not just for you, but also for me. This assemblage is typical for an assemblage that forms during advanced argillic alteration. And here we see a pH temperature diagram that indicates that pyrophyllite forms at low pH at temperatures above around 300 degrees. Typically, in felsic volcanic environments where you have got quite a bit of acidic conditions. And here in this ternary diagram, we see data from largely from felsic volcanic rocks as they become more and more altered due to the removal of alkalis, but also calcium, iron, sodium. Also phosphorus was mobile during this alteration and gave rise to rocks rich in aluminium, but also rich in titanium to some extent. As I said previously, some of these rocks rich in pyrophyllite are being mined because of the abundance of pyrophyllite in these rocks. It is useful for different kinds of industries, like at the Wonderstone mine. This carbonaceous sediment is being mined, and it finds various uses in different kinds of industry. White pyrophyllite derived from intense alteration of felsic volcanic rocks of the Cipher Fontaine Formation are being used as filler in paints or also paper. So this is why we actually have got quite a bit of good exposure in some of these mines, at least for rocks like Wonderstone. Other usages of Wonderstone, well, you may come across them on old cemeteries, because they have been used quite a bit as tombstones, because, well, they consist largely of pyrophyllite, which is very soft. The hardness is just like talc, so you can easily stretch them with your fingernail, and as a result of this, making these tombstones was not too difficult. Now, if I looked at this tombstone a bit more carefully. So here you see the top of the tombstone, you see the nice fine lamination. You see actually cross-section of a ripple mark. So some beautiful preservation of some sedimentary structures in these rocks. But you see, I mean, these rocks crack easily, so they did not really withstand a lot of time on some of the cemeteries that I have come across with regards to the Wonderstone. In the Otto-style area, there are a number of outcrops of this Wonderstone, so these sediments made of pyrophyllite, and well, they have been used, or let's say many people have left their marks in the history. It's of course very difficult to date these markings, but at least with this image we can be certain that that was produced well after the invention of the Volkswagen Beetle. But yeah, I was specifically interested in the carbonaceous matter that you find in these sedimentary rocks, which is finely distributed within the pyrophyllite diaspore matrix. And here we see a map of one of these Wonderstones. What we mapped is a distribution of carbon. So the more bright areas are more rich in carbon. I mean, we also see it from the darker color here in this optical image. The carbonaceous matter, so here we have the Raman peaks of the carbonaceous matter. It's typically for carbon that was subjected to green schist facies metamorphism. Now the carbon, I mean, these rocks are quite dark in color, sometimes almost black. This is because the total organic carbon content in these rocks is up to around 1.5%. So these are, well, black shales, if you like. And the organic carbon isotopic composition is quite negative. Values are as negative as around -45 per mil. And this is a feature that indicates that the isotopic fractionation was part of a biological process. And the microbes that were responsible for this fractionation can probably be found in assemblage of methanogens, so organisms that produce methane in sediment, but also methanotrophs, so organisms that make use of this methane produced by the methanogens. But there's also evidence for the presence of microbes that were sulfate reducers. And the diagenetic pyrite that we find here and there in this Wonderstone, well, the origin is also, can be attributed to the presence of sulfate reducers in these in the setting in which these rocks formed. So what was the environment for the Wonderstone? We think that Wonderstone was deposited in large intracratonic lakes, and these lakes probably formed after or during volcanic eruptions, when we had collapse of large calderas or maybe rifts forming. And it's in these depressions that lakes developed, and it's in these lakes that the Wonderstone was deposited. Because of the evidence of intense alteration, we believe that the waters were very acidic, and modern day example of such an acidic environment would be this crater lake in modern day Indonesia, which is colonized by methanogens, although the pH is pretty low, less than 1. So we also think that it was actually important to have this very acidic alteration because microbial activity requires nutrients such as phosphorus. And we did observe that phosphorus was actually a mobile element during this intense acidic alteration. So low pH alteration was actually a prerequisite for some of this microbial activity in those lakes. I would also like to mention a few regional significances of our work. As I indicated earlier, we obtained ages for the dominion group felsic volcanics of around 2.96 billion years ago. And this age is basically very similar to ages that have been obtained from, here it is, from rocks of the Nzusa group of the Pongola supergroup. And here we have a stratigraphic column of the Nzusa group consisting of sedimentary rocks, mafic volcanic rocks, but also important felsic volcanic rocks higher up in the stratigraphy known as the Agartha Formation. So these rocks have been dated at 2.98 to 2.96 or so. We obtained ages of 2.96 for the Cypherfontaine Formation. So we believe that the Dominion group and the Nzusa group formed in the same kind of overall sedimentary basin at overlapping time intervals. And because, well, we are dealing here with quite thick volcanic successions, several kilometers for the Nzusa group, but also several kilometers for the Dominion group, we believe that the Kapwa craton at around 3 billion years was covered by, well, the world's first large igneous province, which we refer to as a Dominion-Nzusi igneous province. It formed again in this area, but we also actually find rocks of similar age and similar composition as far north as the Murchison Greenstone Belt. So probably this igneous province was much larger in extent, but more work is required. We believe that the volume of this of the volcanic material that erupted exceeds 100,000 cubic kilometers. The aerial extent, as we know, at the moment exceeded 100,000 square kilometers, and the age, well, it erupted over a maximum time interval of around 40 million years. And what gave rise to the extension that led to the Dominion-Nzusa igneous province? Well, there are dike swarms. It's called the Buckblast dike swarm. They have been dated. Let me go back. Blood dikes. Okay, they have been dated at 2.96 or 7, thereabouts. So these have a northwest, southeast orientation. So we believe that maybe sigma 1 was oriented parallel to the extent of the dike swarm. And well, we know that at this time interval, around 2.96, there were important compressional deformation events happening, both in the Petersburg accretional terrain, but also here in the Kimberley accretional terrain. So maybe plate margin processes along the Kapwal craton at the time may have given rise to rifting, extension, and then eruption of this large igneous province. The dominion group underlies the Witwatersrand supergroup. So we did develop some kind of relationships between the two. In this photograph, what we see are felsic volcanic rocks of the Cipherfontaine Formation, which are erosively overlain by relatively thin conglomerate that is overlain by shales of the Parktown Formation. Regionally, we can observe an angular unconformable relationship between the Dominion group and the Westrand group. And at least our work did allow to somewhat more tightly constrain the deposition of the Westrand group because it must have started after the volcanic activity dated at 2.96. So Westrand group deposition started at some point, maybe 2.95 or even younger. So yeah, well, so this is my last slide, which tries to summarize our new views on the Dominion group. So the Dominion group, as it has been known for a long time, is a bimodal volcanic succession, but it is younger than was previously believed. It was deposited between 3 billion years and 2.96 billion years on basement that had a prominent 3.07 age component, ages that seem to record highly evolved felsic plutonic magnetism that gave rise to tin granites. We believe that the Dominion group, together with the Insusa group, represents the first large igneous province and was followed later on then by these other large igneous provinces, such as the Ventersdorp lip, the Bushveld lip, the Karoo lip. So well, here we think we are observing the first of these large igneous provinces. The Dominion group, well, preserves a kind of a fossilized volcanic landscape in an intracratonic setting where lakes developed, where intense alteration gave rise to paleosols, where intense alteration gave rise to leaching of various elements that ended up in these low pH lakes that supported microbial life already 3 billion years ago in an intracratonic setting. So we believe that already as early as 3 billion years ago, volcanic lakes were viable niches for life, even in quite extreme environments of very low pH, maybe as low as 1. And I think that ends this presentation. So I hope I was able to give you a few new views on the Dominion group, which from our perspective had not really been studied, for 13 years or so, despite them actually recording very interesting geological phenomena and processes. Thank you.
Thank you so much, Axel. That was really fantastic. I can see there's some questions already coming through on the chat, but perhaps let's take some questions from the room first. Are there any questions?
Right, let's start with Wits. That's all great, great presentation. Thank you. And I like the model. We've got the Nsuzi Dominion large igneous province. What I'd like to know is in the Nsuzi group, it's clearly there's more plastics coming in, interbedded with the extrusives in the Nsuzi when compared to the Dominion. How do you interpret that? Is that a preservation issue? Or is there some lateral differences in precision relative to a coastline? Why do you think there's more plastics in the Nsuzi?
Well, probably the Nsuzi group records a much larger time interval. It probably formed at least over 20, maybe 30 million years. And obviously magmatism is frequently not continuous over such a long time interval. It's relatively focused during narrow times. So probably what we see in the Cipherfontaine Formation is a relatively narrow time interval that gave rise to a thick pile of volcanic rocks, whereas in the Nsuzi group, we had many more breaks in the volcanic activity and deposition of sediments in between.
Thanks.
Okay, Rob, nice and loud if you can, so the microphone can pick you up.
Okay. Actually, you said that the crater was affected by deformation and presumably metamorphism at about 2.96 in the northern part. In your circumdata set, we show two age groups, one at 3.1 and one at 2.9 in the volcanics. And with two age groups, there are always two interpretations possible. The older age being inherited and the younger age being magmatic, or the older age being magmatic and the younger age being metamorphic. How can you be sure that the younger age of the volcanics of the remaining group is not metamorphic?
Well, I mean, the thing is, you know, like there are some, I didn't show it, there are also some Ventersdorp age intrusions. And these Ventersdorp age intrusions, well, they have a circumference of 2.78 or something like this. Well, they also contain xenocrysts of these older units of 3.07, but also of 2.96. And these rocks have not been subjected, at least not in this area, to high-grade metamorphism.
So, Axel, you'd say that all those 3.1 billion year old ages in the Dominion are xenocrystic ages?
Yes.
Lawrence?
Yeah, so, you know, what's really fascinating about this kind of talk is obviously just highlighting again the fact that there are minerals, trichal minerals, which are unequivocally trichal, because unlike when Phil and I worked on these things 30 years ago, we didn't have any ages on these, but now, yeah, they're clearly trichal because they've been dated. We've got the trichal cassiterite and the trichal uraninite, and there are a suite of other minerals which you alluded to as well.
Yes.
It clearly indicate that they would have come from a highly evolved granitic source, but it's more than that. It must be a granitic source that was actually mineralized,
Yes.
because you don't find uraninite or cassiterite occurring in granites.
No, that's
other
right.
than in these sort of high-level, hydrothermally altered cupular zones of these granites, which typically does suggest that the terrain is actually mineralized.
Yes.
Even to the point that there may have been ore deposits, primary, not necessarily porphyry style, but granite-hosted type mineralization in the basement. A lot of which obviously was eroded away, and now sits in both the Dominion and the Pongola. You can't actually see it anymore. But so it begs the question as to how fertile the whole source area was, and whether there wasn't something fairly specific about the fertility of that region that gave rise to these unique Dominion type packages with all the uranium and the gold and everything else that's in them. So if that was the case, what would be specific about the source area in terms of its tectonic setting that would explain that? I mean, you mentioned, you know, rift environment. The fact is, you've got these granites which were placed literally the weekend before the Dominion started being deposited. So they're very similar in age. You know, these granites were coming in, they were being unroofed, and sedimentation was taking place already. So what was the environment that those kind of processes took place in?
Well, I mean, there was quite a big time gap between deposition of the Dominion group and the emplacement of the granites. I mean, the granites are 3.07. I mean, you dated one granite of 3.03.
Yeah.
Now, the age of deposition is younger than 2.995. So there are several tens of millions of years in between. Well, what gave rise to the mineralization that must have been present in these granites at that time? Well, I don't know. We need to ask ourselves, what was the reason for the tin granites, in Swaziland, to become enriched in these elements.
So that was what I was going to come to. So if you look at sincerity, in Swaziland, tin granites, and these things have to be full of cassiterite as well. It seems as though there may have been some sort of tin province.
Yes.
Tin granites in the Copper Craton.
That's right.
That gave rise to the tribe of cassiterite not only in the west, but way out in the east as well.
Yes. So interesting questions, that are being raised from this kind of work.
Okay. Jill, we're going to come to you in a second, but I can see lots of questions coming through here on the chat. So let's see if we can.
Just before you, it's related to that.
Okay, go for it.
What's the final age that we got for the younger granites in copper contain?
It was 2.78, I think, wasn't it? Really that young. But those were obviously intrusive into the community.
Okay.
All right, so here we have a question from Wolfgang Meyer. Thanks for joining us, Wolfgang. Could you explain your evidence for an SCLM origin of the mafic volcanics?
Yeah, well, I mean, this has been proposed quite a long time ago already in articles by Booney Marsh, who worked on these rocks, but also, I can't remember if Kent Condy was also working on some of these rocks.
Yeah, he was.
Yeah, he was, yeah. So, I mean, the thing is, when you look at the trace element patterns of these rocks, well, they all show more or less identical trace element patterns. They all have an enriched component. You don't see both depleted and enriched trace element patterns. And so the homogeneity of the signature, the chemical signature of these rocks, seem to indicate that, well, the source must have also been relatively homogeneous, an enriched source, which kind of fits with subcontinental lithospheric mantle.
Okay, then let's see. A question from Anthony Rutherford. Have you noted any uranium or uraninite in intervolcanic sediments?
No, there's no enrichment.
Okay. And then a question from George Henry. You mentioned low gold content in the basal conglomerates. Is there organic matter in the conglomerates? And is there anomalous gold in your organic mats?
Well, we have searched quite a bit for the organic matter in these conglomerates. And I must say there is a little bit, but it's not.
Always nodular. There are no seams that I can see in there.
Yeah, no, there is not a lot, also not a lot of nodular carbonaceous matter. There is a little bit, but I'm not quite sure, it could have been derived. The thing is, what we are seeing in the Cypherfontaine formation are organic rich shales. They must have produced quite a bit of hydrocarbon. And so maybe some of it could even have ended up, at the unconformity due to faulting and stuff like this. So I'm not sure, but yeah, there is not a lot of organic carbon in these rocks. A little bit, but yeah, we haven't figured out how it came in there.
Okay, well, thank you for all your interaction online with questions. I don't see any more from the audience. Are there any more questions here live? Okay, then it looks like, Axel, you're off the hook. Thank you very much for a very fantastic presentation. And next week we have a PhD student in the school, Sike Muhuba, who will be speaking about hydrogeological characterization and groundwater pollution around the Tasepunt nuclear site in the Eastern Cape. So that promises to be a very interesting talk about groundwater. So I look forward to seeing you all there. Same time, same place, next week. Thanks, everyone, and thanks, Axel.